Hi there, I am Bhaskar and I will present our work on robust non-parametric regression via incoherent subspace projections done with my collaborators Subhajit and Purushottam at Indian Institute of Technology, Kanpur. The code for this paper is available at Purushottam's GitHub. We present APIs, alternating projection onto incoherent low-rank subspaces as a unifying principle for designing robust algorithms for linear regression, kernel regression, and sparse signal transforms. For a real-valued regression problem on n data points with responses arranged in the vector A star, suppose an adversary introduces corruption B star so that observed responses are y equal to A star plus B star. The question of recovering A star from y captures several robust regression tasks for which our method APIs guarantees exact recovery of A star even against fully adaptive adversaries. The key to APIs is subspace incoherence. Two subspaces are said to be mu incoherent if projection of any vector from one subspace onto another diminishes its squared norm by at least a factor of mu. The figure on the left shows two incoherent subspaces A and B that are nearly orthogonal with mu close to 0. In contrast, the figure on the right shows two coherent subspaces with mu close to 1. To see why incoherence is useful, let y be A star plus B star, where A star and B star belong to perfectly incoherent subspaces A and B with mu equals 0. Let A naught initialize to 0 be our initial guess of A star. We note that projecting y minus A naught onto subspace B yields B star, and then projecting y minus B star onto A yields A star. Thus, exact recovery in this toy setting takes just 2 iterations. In real-life applications, we don't know the exact subspaces to which A star and B star belongs, but are often assured that they come from known union of subspaces, say script A and B. For example, if A star is known to have a sparse Fourier transform, then it belongs to the union of n choose S many rank S subspaces, each spanned by some S of the Fourier basis vectors. Similar is the case if B star is known to be k-sparse. A natural extension of subspace incoherence tells us when two union of subspaces are mu azimuth incoherent. Given the corrupted responses y and operators that project onto subspace unions script A and B to which A star and B star belongs, APIs initializes A naught, its estimate of A star, to 0. At time t, projecting y minus at onto script B gives us a better estimate bt plus 1 of the corruption. Next, projecting y minus bt plus 1 onto script A gives a better estimate of at plus 1 of the clean responses. These projection operators can be efficiently implemented for several applications. APIs probably converges to A star at a linear rate whenever script A and B are mu azimuth incoherent with mu less than 1 by 9. This is true even if the adversary is fully adaptive and can decide the corruption B star with full knowledge of A star. We show that azimuth incoherence holds whenever the subspaces in script A and B have low rank, say less than S and K respectively. The requirement mu less than 1 by 9 imposes an upper limit on these ranks, deciding the breakdown point for APIs. APIs can also handle misspecified models when A star belongs to script A only approximately, and even if only local azimuth incoherence is assured. We derive breakdown points for APIs for a range of robust regression tasks. APIs can even tolerate dense corruptions where B star has non-zero entries corrupting all the responses, provided B star has a sparse representation in some suitable basis, for example, in the last row of the table. This will be useful for image denoising. Classical linear regression has applications in diverse areas. It takes a feature matrix X, a response vector Y, and minimizes the least square loss to find a linear model W hat so that Y is approximately equal to X transpose W hat. However, the least squares estimate is written. Let a gold model W star generate the clean responses A star equal to X transpose W star. But K of them are corrupted so that we observe Y equal to A star plus B star. As the figure shows, even a single corrupted response can arbitrarily shift the model W hat learned by the least squares. In contrast, APIS offers recovery of the gold model W star even if a constant fraction of responses are corrupted. To apply APIS to robust linear regression, let A star equals X transpose W star for some gold model W star and the corruption B stars be K sparse. That is, K responses are corrupted. In this case, script A is simply the row space of the feature matrix X and projection onto script A requires a simple least squares estimate. Script B here is a set of all K sparse vectors and hard thresholding operator that preserves the top K coordinates by magnitude and sets the rest to 0 projects onto script B. These projection steps are implemented efficiently in standard libraries. In the experiments with synthetic data where 20% responses are corrupted, APIs shown in deep blue offer the most rapid convergence among all the methods. On the left hand side, we see recovery up to machine level precision when no Gaussian noise was added, while on the right hand side, Gaussian noise was added even to the clean responses. In robust kernel regression using Mercer kernel K, for example, the RBF kernel, clean responses A star equal G alpha star, where G is the n cross n gram matrix and alpha star belongs to the span of top S eigenvectors of G. APIS also works if A star is only well approximated in this span. Here, script A is a span of the top S eigenvectors of G, which can be efficiently found. Projection onto script A is then a linear operation. For K sparse corruptions B star, projection onto script B is done using hard thresholding. The paper argues that restricting alpha star to the span of top few eigenvectors does not affect the universality of kernels such as RBF kernel. APIS shown in deep blue offered the base test RMSE 2 to 5 times smaller than any competing method when non-parametrically recovering sinusoidal, polynomial, hybrid functions. 5 to 10% of the responses were adversarially corrupted by flipping their sign, shown as red crosses. APIS also offered test RMSE up to 10 times smaller than the competing methods for non-parametric recovery of multivariate sinusoidal functions. In sparse signal transforms, the clean signal A star is M alpha star, where M is a design matrix of the transform, such as Fourier or Hadamard, and alpha star is a sparse vector. Script A here contains n choose S many subspaces, each of rank S. Using the orthonormality of M, projection onto script A can be implemented in order n log n time using fast versions of these transforms and hard thresholding. We considered K-sparse corruptions where B star has only K non-zero entries and hard thresholding can project onto script B. We also considered dense corruptions where B star is dense. B star is a dense vector but with a sparse representation in some other basis such as noiselet. In this case, projection onto script B is similar to script A. In the first image denoising task, 20% pixels are adversarially corrupted in each image. APIS shown in the last column offered visually superior recovery and up to 25% better PSNR and SSIM than the next best method DNCNN SP, that is deep learning based and needed 6 hours of training. In the second task, all pixels of an image were corrupted by superimposing a dense checkerboard pattern. APIS shown in the last column recovered fine details of the original image, offering 14% better PSNR and SSIM than the next best method DNCNN block. Note that checkerboard patterns are dense but have sparse representation in other bases such as wavelet. In conclusion, we present APIs as a unified principle for designing robust non-parametric regression algorithms. APIs offers explicit background point against fully adaptive adversaries. In experiment, APIs offered fast convergence and superior test RMSE on robust linear and kernel regression tasks, as well as far superior recovery compared to state-of-the-art image denoising algorithms. I look forward to discussions and answering any questions. Thank you.